Hi, I'm Daniel Chan from UNSW Sydney. Welcome to another adventure in pure mathematics. One of the principles of affine algebraic geometry is that the algebra of the coordinate ring captures all the geometric information that you would want. So in this video here, I want to give an example of this by showing how points manifest themselves algebraically. To set up our notation, we'll start with an algebraically closed field F. And we're going to work in the set of n tuples, which is commonly called affine n space in the language of algebraic geometry. So we use this notation here, a to the n. That's the standard notation in algebraic geometry. And the objects of study in algebraic geometry are solutions to polynomial equations. So let's consider R polynomials, f1 up to fr, with coefficients in f and in variables x1 up to xn. So we can look at the common solutions to all of these polynomial equations. So setting these all equal to 0. And that gives you the affine variety that we denote by v, f1 up to fr. So in other words, just the set of all n tuples alpha, which are the common zeros of f1 up to fr. Algebraically, we associate to these polynomials the following ring, which we call the coordinate ring. It's the polynomial ring f x1 up to xn, quotient out by the ideal generated by f1 up to fr. And the motivation for this, remember, is that one should think of elements inside here as being polynomial functions on this variety. You have to factor out these polynomials because when you restrict to this set here, there's 0. And the question that I want to raise today, which is very natural, is, well, if this is supposed to capture all the geometric information about this, how do you determine the set of points inside here algebraically just from this ring? So this is a very natural question, and it has a very nice answer, which I want to show to you now. So the case that we want to have a look at first is the simplest case where there are no relations. So in other words, we don't have any polynomials involved, and we just look at the whole affine space, and the coordinate ring is just the polynomial ring here. So what can you do with a point on this affine space? So just an n-tuple alpha. Well, the point is that you have a substitution homomorphism. Given any polynomial in x1 up to xn, if you're given an n-tuple, you can substitute these variables for these variables, the corresponding coordinates of alpha. So the polynomial f just goes to f of alpha tilde. And you should have learnt in your first modern algebra course that this is a ring homomorphism. In fact, it's an F-linear ring homomorphism. So another way to state what this ring homomorphism does is to look and see what it does to, firstly, the coefficients, the scalars, and each of the variables. Once you know that, you know what the whole homomorphism is, because the ring homomorphism is additive and it's also multiplicative. If you have beta, that's a constant function. It doesn't matter what you're substituting, you'll still get beta. So the constant beta gets sent to beta. What about xi? Well, here you just substitute in the corresponding entry of alpha tilde. So that's just alpha I. And now this leads to the first theorem, which gives us an algebraic characterization of all the points of the affine n space. It's as follows. It's written in terms of a bijection. We have a bijection between the points of affine n space and these gadgets here, F-linear ring homomorphisms from the polynomial ring to F. So we have a map from here to here. Given an n-tuple, you send it to the corresponding substitution homomorphism. And it turns out that that's a bijective map, and it's quite easy to show it's a bijection by constructing the inverse. And if you want to work out what the inverse is, it's quite clear from this formula here. If you know the map, how do you recover this alpha tilde? You just need to recover all the alpha i's. And where do the alpha i's come from? They're just the images of the xi's. So that means the inverse map is given by sending this phi to the n-tuples whose coordinates are 5x1 all the way down to 5xn. So the points of affine n space manifest themselves algebraically as just F-linear ring homomorphisms from this polynomial ring to F. So let's look in the general case where you have this quotient ring here instead. So now we want to restrict this to just the variety where F1 to Fr are 0. That's the variety F1 to Fr. So what happens then? So let's see what happens to F1 to Fr if you restrict to such a point. Then since it's 0, the values of F1 to Fr get sent to 0. So they're precisely the homomorphisms from this polynomial ring to F, such that this whole ideal gets sent to 0. And if you're good with your universal quotient property for quotient rings, you see that this is precisely the F-linear ring homomorphisms from this quotient ring R to F. So we see now this is the first incarnation of the points of this variety in a purely algebraic way, just using the coordinate ring. It's simply just the set of F-linear ring homomorphisms from R to F. We actually have a second algebraic incarnation of points, and this follows from what's usually associated to a part of Hilbert's Nullstellensatz. So Nullstellensatz is a German word. It refers to Nullstellen is the zeros, and Satz just means the theorem or principle. So sometimes this is called the zeros principle. This Hilbert's Nullstellensatz is one of the pillars of algebraic geometry, and part of it states the following. You look at this coordinate ring R, and you pick an ideal M which is maximal, and by that I mean maximal not equal to R, of course. What can you do? Well, R mod M, since this is maximal, is a field. You have a quotient map from R to R mod M, and since this is the quotient of the polynomial ring with coefficients in F, you can map F to R. And it states that this morphism of fields from F, this field here, to this field here, is an isomorphism. So what can you do with this? Well, you can do the following. In this case, we have a bijection from the set of all F-linear ring homomorphisms from R to F. So remember, this was our first algebraic incarnation of the set of points of the variety. This is in bijective correspondence with just the maximal ideals inside R. And it's quite easy to say how that works. Well, given such an F-linear ring homomorphism, what's the corresponding maximal ideal? Well, since this ring homomorphism, of course, has to be surjective, phi, if you map this to kernel of phi, this kernel of phi has to be a maximal ideal by the first isomorphism theorem. This map has to be surjective, so the quotient has to be a field when you do R mod the kernel of phi. So this is maximal. So conversely, if you're given a maximal idea, what does this tell you? Basically, the quotient is f. It's isomorphic to f. So the quotient map from R to R mod M, R to R mod M is essentially an F-linear ring homomorphism from R to F. So this is our second incarnation of points on the variety, and it's just a set of maximal ideals inside our coordinate ring R. So I should make some remarks about these two. So the first point is that the second theorem depends critically on the fact that our field F is algebraically closed. Our first theorem does not. But the second theorem has its own advantages as well. You see, the difference in this description of the set of points and this one is that this one here makes no mention of the field F at all. You didn't have to specify that we're working over the field F and that's what we're concentrating on. This is completely ring theoretic. And so often this is the way to go when you want to try to generalize to more complicated algebraic objects such as schemes. I hope you enjoyed this adventure in pure mathematics.